Picture a country with no permanent rivers, no freshwater lakes, a sky that delivers barely 4 inches of rain each year, and a sun so intense it can vaporize standing water before it has a chance to soak into the ground. Now picture that same country quietly executing one of the most complex water management systems ever attempted by any nation on Earth. A system so counterintuitive that when engineers first proposed parts of it, the idea sounded more like science fiction than serious policy. This is Strategic Dynamics Edge, and today we are going deep on how Saudi Arabia is fighting one of the most serious resource crises of the modern era, and what they have quietly built beneath the desert to survive it. If you're watching this for the first time, subscribe right now and hit the bell icon. We cover the stories behind major global decisions that most channels never touch. Share this video if it teaches you something, and drop a comment below when we get to the part that surprises you most. Now let us get into it. Saudi Arabia presents what might be the most dramatic gap between demand and natural supply of any major nation on the planet. The country sits at the heart of the Arabian Desert, one of the driest regions on Earth. Average rainfall across most of the country hovers around 4 inches per year, and in some interior zones, it is even less than that. There are no permanent rivers running through the landscape. There are no significant natural lakes. The heat is relentless, with summer temperatures regularly exceeding 122 degrees Fahrenheit in many parts of the country. And yet, tens of millions of people live here. Enormous, modern cities have risen from this desert. Skyscrapers, industrial zones, agricultural operations, and annual pilgrimages that bring millions of visitors to Mecca and Medina all demand the same thing in enormous quantities: water. For decades, Saudi Arabia has relied primarily on what lies beneath the surface. Geological surveys estimate there are around 26 trillion gallons of water stored in underground aquifers across the country. That sounds like an abundance that could last generations. The problem, according to hydrologists and water scientists, is that the overwhelming majority of that water is what researchers call fossil water. This is ancient water that accumulated underground thousands of years ago during a geological era when the climate of the Arabian Peninsula was far wetter than it is today. Back then, rainfall soaked into the earth over vast stretches of time and filled these underground chambers. Once that water is pumped out, it does not come back. Today's scarce rainfall does not come close to replenishing what was stored over millennia. According to available data, only an estimated 739 billion gallons per year of Saudi groundwater qualifies as renewable, meaning it is naturally refilled through modern rainfall at a rate that can sustain long-term withdrawal. Everything else is essentially a finite inheritance being spent down. Saudi Arabia's own water consumption figures have consistently outpaced that renewable threshold by a significant margin, driven by the demands of a growing population, large-scale agriculture, industrial use, and urban expansion. Water scientists who study the region have raised alarms about the trajectory of fossil water depletion for years. In response to this pressure, Saudi Arabia has made significant investments in capturing whatever rainfall does occur. The country has constructed 522 dams since the early 2000s, according to official reporting. In a desert nation, these structures serve a specific and critical function. They are not built to hold back year-round rivers. They are designed to capture the sudden, intense bursts of rainfall that occasionally sweep through the region and rush through dry riverbeds called wadis. Without these dams, that water would disappear almost immediately through evaporation or runoff. The collective storage capacity of these 522 structures is reported at approximately 650 billion gallons. The dam network in the Mecca region alone spans 60 structures with a combined capacity of over 232 billion gallons. But capturing intermittent rainfall, while important, addresses only a fraction of the country's needs. The gap between what the dams collect and what the population consumes is enormous, and the fossil water reserves, however vast, are being drawn down faster than any natural process can restore them. This is the reality that pushed Saudi planners and engineers toward a far more radical solution. Saudi Arabia borders two bodies of saltwater, the Red Sea to the west and the Persian Gulf to the east. Seawater is not drinkable in its natural state and cannot be used for agriculture at scale, but it is effectively unlimited. The technology that makes it useful is called desalination, a process that removes salt and other dissolved minerals from seawater to produce fresh water safe for human consumption and irrigation. Saudi Arabia did not just adopt desalination as a supplemental measure. According to available infrastructure data, the country has made it a foundational pillar of its national water strategy, growing from minimal desalination capacity in the 1980s to 43 operational facilities by 2024. One facility on the eastern coast, recognized by Guinness World Records as the largest hybrid thermal and membrane desalination plant in the world, reportedly produces around 792 million gallons of fresh water every single day. That is the output of one plant. The scale of Saudi Arabia's desalination infrastructure has made it the leading producer of desalinated water on the planet by most industry measures. It is a remarkable engineering achievement, but it comes with significant costs and trade-offs that engineers and policymakers openly acknowledge. Desalination is an energy-intensive process. Depending on the technology used and local energy costs, producing desalinated water can cost anywhere from 3 to 10 times more than drawing from a conventional freshwater source. Saudi Arabia's fossil fuel wealth has made this economically manageable, but the cost remains a meaningful constraint. There is also an environmental consideration. The desalination process produces a highly concentrated saltwater byproduct called brine, which must be carefully managed. If discharged improperly into coastal waters, brine can damage local marine ecosystems by raising salinity levels and reducing oxygen availability for sea life. Saudi Arabia has invested in brine management systems, though experts continue to monitor the long-term ecological impact as production scales up. Producing fresh water on the coast does not automatically solve the problem for inland cities. Riyadh, the capital, sits deep in the interior of the country, hundreds of miles from the nearest coastline. Moving water across those distances in a desert environment presents its own engineering challenge of the highest order. Above-ground pipelines or open channels in a climate that regularly exceeds 122 degrees Fahrenheit would lose an unacceptable percentage of water to evaporation and would be highly vulnerable to the physical stress of extreme temperature swings, blowing sand, and occasional flash flooding. Saudi engineers addressed this by going underground. According to reporting on the Saudi Water Authority's infrastructure, the country has developed a network of buried high-pressure pipelines that stretches approximately 8,700 miles end to end. To put that distance in perspective, the Nile River, the longest natural river on Earth, runs approximately 4,135 miles. Saudi Arabia's underground water transport system is, by that comparison, more than twice as long. These are not shallow pipes. Many sections run deep beneath the surface, shielded from heat, protected from contamination, and engineered to maintain stable pressure across enormous distances. The pipes themselves, some exceeding 2 meters in diameter, required precise installation to avoid pressure failures or structural collapse underground. Construction was, by any reasonable measure, an extraordinary undertaking. In the western part of the country, the pipeline network had to pass through the Hijaz Mountains. Engineers used tunnel boring machines and controlled explosions to carve through dense granite and limestone formations that resisted conventional excavation methods. In the desert interior, shifting sand dunes, dust storms, and the physical danger of working in extreme heat meant that construction teams regularly adapted their schedules to operate during cooler nighttime and early morning hours. Deep trenching and soil stabilization across thousands of miles of unstable terrain required engineering solutions developed specifically for this environment. The result is an infrastructure system that functions, in practical terms, as an artificial underground river, invisible from the surface, moving desalinated water from coastal production facilities to cities, industrial zones, and agricultural regions across the entire country. It is one of the most ambitious water infrastructure projects ever attempted, and it operates largely out of public view. Now, here is where the strategy takes a turn that initially seems puzzling. After spending billions of dollars to desalinate seawater and then transport it hundreds of miles through this underground network, Saudi engineers have in some cases pumped portions of that water back into the ground deliberately. Not because of an accident or a leak, not because something went wrong, but as part of a planned intentional storage strategy. This is what confused outside observers when details of the program first emerged, and it is the part of the story that requires the most context to understand. Saudi Arabia has announced, under its Saudi Green Initiative, a goal of planting 10 billion trees across the kingdom over coming years, according to official government statements. The initiative also sets a target of protecting 30% of the country's land from desertification and converting approximately 184 million acres of degraded soil into productive land. The environmental science behind large-scale tree planting in arid environments supports several claimed benefits. Trees reduce surface temperatures in their immediate vicinity. Studies suggest that significant urban tree cover can reduce concentrations of fine airborne particles, with some researchers estimating potential reductions in PM 2.5 levels of up to 20% under favorable conditions. Some climate scientists also note that large-scale vegetation in historically dry regions can, over time, influence local humidity and rainfall patterns, though the scale and timeline of such effects remain subjects of ongoing research. The practical challenge is straightforward. 10 billion trees in one of the driest environments on Earth need water, not occasionally, continuously, at a scale that unpredictable rainfall cannot guarantee, and that rapidly depleting fossil aquifers cannot sustain indefinitely. And surface storage in this climate is deeply inefficient. Open reservoirs in the Saudi desert lose an estimated 20% or more of their stored water to evaporation annually, according to figures cited by water researchers studying the region. For a water supply system expected to support both a growing population and a generational ecological restoration program, that level of loss is not acceptable. Underground storage eliminates the evaporation problem almost entirely. By injecting treated, desalinated water into managed aquifer recharge systems, engineers are essentially using the cool, stable geological formations beneath the desert as a vast, insulated storage tank. The water sits underground, protected from heat and contamination, available for withdrawal whenever it is needed, whether that is next month, next year, or several decades from now. This approach, which water engineers refer to as managed aquifer recharge, is used in various forms around the world, but the scale at which Saudi Arabia is applying it, combined with a desalinated source and a pipeline network of this length, represents a genuinely novel application of the concept. This is the logic behind burying the water. It is not a paradox or a mistake. It is the most rational storage solution available given the physical realities of the environment. The desert geology becomes the infrastructure. The underground formations that once held fossil water for thousands of years are now being deliberately recharged, to whatever extent is possible, with water produced by the desalination system. The goal is not just to meet today's demand, but to build a buffer for the demands of a future that, according to Saudi government projections, will require significantly more water than the country currently manages. What Saudi Arabia has assembled, viewed as a complete system, is something genuinely unprecedented in scale. Hundreds of dams capturing seasonal rainfall before it evaporates, dozens of desalination facilities converting ocean water into fresh water at rates measured in hundreds of millions of gallons per day, an underground pipeline network spanning a distance more than twice the length of the Nile, and a managed underground storage program designed to bank water for a green future that is already being planted tree by tree across the desert floor. Each component addresses a different dimension of the same fundamental problem. Together, they form a water security architecture that no single approach could achieve on its own. It would be incomplete to present this without acknowledging the significant challenges that remain. Desalination at this scale is expensive and energy intensive. Transitioning the energy supply for desalination toward renewables is a stated goal, but it is a work in progress. Brine management requires continued investment and monitoring. The fossil water that was extracted over past decades is gone and will not return on any human timescale. The 10 billion tree initiative is ambitious by any measure, and the outcomes in terms of climate and ecological impact will take years, possibly decades, to be properly assessed. These are not reasons to dismiss what is being built. They are reasons to follow it closely. Water scarcity is not a challenge unique to Saudi Arabia. Dozens of countries on every continent are approaching or have already crossed thresholds where natural water supply cannot keep pace with demand. The engineering strategies being developed and scaled in the Arabian desert, from large-scale desalination to underground water banking to the deliberate greening of arid land, are approaches that will matter far beyond the borders of any single country. What Saudi Arabia is doing is, in many respects, a large-scale experiment in how a technologically capable society responds to an existential resource constraint. The results will be studied and referenced for a very long time. This is Strategic Dynamics Edge. If this story made you think differently about water, about infrastructure, or about what nations are capable of when they have no other choice, then take a moment right now to like this video and share it with someone who should see it. Leave a comment below with the country you think faces the most serious water crisis today. We read and respond to comments, and we want to know what you think. Subscribe and hit the notification bell so you're always first when we publish. We will see you in the next one. A final note for transparency. The figures and program details referenced in this video are drawn from publicly available reporting and official government statements at the time of production. Infrastructure projects of this scale evolve over time, and specific numbers may be updated as programs develop. This video is produced for educational and informational purposes only,